Good afternoon. I'd like to welcome all of you to the latest in a series of science and tech talks sponsored by the Physical Biosciences Division. And here to introduce our speaker is one of our senior scientists, Heinz Frey.
Thank you, Jonathan. Well, it's a pleasure to introduce Ian Sharp. Ian got his PhD from UC Berkeley here in 2006 in material science and engineering. He has also a bachelor in degree in chemical engineering. He was with Eugene Haller in the electronic materials group here at LBL doing his thesis work. He got then von Humboldt fellowship, junior fellowship, and joined the Walter Schottky Institute at Technical University in Munich, where he worked on chemical and electronic properties of biofunctionalized semiconductor materials. In 2009, he was appointed at TU Munich to the Institute for Advanced Studies as a Karl Linde Fellow, and that allowed him to start his own research group. He expanded his work into bioinorganic hybrid materials, including enzymes on things like silicon carbide, gallium nitride, diamond, looking for understanding these hybrid materials for, use-inspired applications like, for example, biosensors. And his techniques are high-end electrochemical methods, as you will see, and dynamic spectroscopies. 2 years ago, we were lucky to lure him to Berkeley as a staff scientist in the new Joint Center for Artificial Photosynthesis. He's in the Interface project. That's one of the 8 large projects of JCAP. And I think today he's going to talk mostly about research he has done at the center. The title of his talk is Functional Semiconductor Interfaces for Solar Fields Generation. So please welcome Ian Sharp.
So thank you, Heinz, for the introduction. Is the microphone working? Okay. So yes, today I'll be discussing some of the recent results that we have within the Interfaces project at JCAP, and in particular on interfacing semiconductors, both photoanodes and photocathodes, to catalysts that we use to drive water oxidation and hydrogen production, respectively. The ultimate goal of our research is to mimic the process of natural photosynthesis, which in its basic form is the capture of photons and conversion of that energy into a chemical fuel, or store that energy in chemical bonds. Nature does this in a highly efficient way. Once a photon is captured, charge separation and conversion happens with a very high degree of efficiency. And so we would like to take inspiration from this and mimic that process. And we are doing this with inorganic semiconductors as the light absorbers in this case. So there's a few approaches to this. One of them is based on using a single semiconductor. On one side of it, you can put a catalyst for water oxidation. And on the other side, you can put a catalyst for hydrogen evolution. The problem associated with this is that you have to first overcome the thermodynamic potential for water splitting, and then also have enough extra potential to work at the overpotentials required for the catalysts to operate. This means that the band gap of that semiconductor you use is prohibitively large, typically, because you lose a large fraction of the solar spectrum. Another approach is to actually more closely mimic natural photosynthesis by using 2 separate light absorbers. So this is a 2-photon-based process in which one of the semiconductors is optimized for water splitting and the other one for fuel formation or hydrogen production, such as shown on the bottom figure here. I'll go into more details of exactly how that works in just a moment. So just to give the JCAP mission, which I think is important in the context of this talk, and I'll actually even read it, it's to demonstrate a manufacturable, scalable solar fuels generator using Earth-abundant elements that with no wires robustly produces fuel from the sun 10 times more efficiently than current crops. So the most important thing here is that we need to do this in a manufacturable and scalable way, which necessitates that we use Earth-abundant elements. That means that platinum, iridium, ruthenium, some of the best catalysts for doing these reactions are automatically out. So we have projects within JCAP that are actively seeking to develop these new catalysts. And within our project, we're seeking ways to, with high degrees of efficiency, interface these to the semiconductor light absorbers without losing charge. Okay. Energetics of these systems are going to come up multiple times throughout this talk, so I'm going to introduce this, this energy scheme for the combined photoanode photocathode construct that describes the systems that we're looking at. So the photoanode is an N-type semiconductor. That means the majority carriers are electrons within the material. So this dashed line here represents the Fermi energy. The bottom line here is the valence band edge, and the top line is the conduction band edge. So in this material, as you make an electrolyte interface between the semiconductor and the electrolyte, upwards band bending occurs. So you see these bands are bent upwards. This is a macroscopic electric field. So when we photoexcite carriers, so a photon is absorbed here, an electron is excited from the valence band to the conduction band, there's an electric field that drives those electrons, the majority carriers, away from that interface, and the minority carriers, which are holes, to the interface. These holes can then be transported to a catalyst and drive the water oxidation reaction, which generates our protons. These protons are then transported through a conductive membrane to the photocathode side, which operates in a similar fashion, but in this case it's a p-type semiconductor. That means the majority carriers in that material are actually holes. The Fermi level lies closer to the valence band, and under photoexcitation, this electric field at the surface that's generated by the semiconductor electrolyte contact leads to, again, minority carriers. In this case, these are electrons being transported onto the catalyst that's attached to the surface and then forming hydrogen. That's not the overall goal of JCAP. That's the short-term goal of JCAP. The overall goal is to replace that hydrogen evolution reaction with a fuel-forming reaction. This is substantially more complex. It involves many more protons, many more electrons, and catalysts that can support all of the intermediate steps of this process. Nevertheless, an important point to note is that this photoanode side remains effectively the same, because water is the only abundant enough source of protons and electrons that we need to drive the reaction. So work on the photoanode side is crucial regardless of what the eventual fuel that you form actually is. So there's a number of scientific gaps associated with this device. We can draw these pictures quite well. We can envision in our minds how such a system would work. But in reality, we have a number of problems. With the semiconductor itself, it has to conform to three major things all at once. It needs to be stable under the conditions for photocatalysis to occur. The band gap has to be suitable for capturing solar light, the solar spectrum, with a high degree of efficiency. And the positions of those valence and conduction bands have to be well suited for driving the reactions that we desire. Often, these materials also require high surface areas to improve efficiency. From a catalyst standpoint, we already mentioned we need non-precious metals, so new catalysts must be developed. These catalysts must be stable at the pH of operation. That means both the catalysts and the semiconductors under similar pH conditions must be stable. That's not an easy task to fulfill. And for CO2 reduction, we need to develop new catalysts. In particular, molecular catalysts are thought of as being some of the most promising for this case. And so for a large fraction of this talk, I will talk about the interfacing of molecular catalysts on the semiconductor surfaces. Then when we bring these two things together, we need to maintain efficiency. So if interfaces are essential to the success of a project such as this. You can have a very highly functioning catalyst, a semiconductor that's optimized for solar absorption and with bands in the correct positions, and you bring them together and you create interfacial defect states that lead to charge recombination and complete efficiency losses that dominate the performance of the device. So we need to engineer these interfaces with a high degree of precision. Okay, let's get to some research and some recent highlights from the Interfaces project at JCAP. I'll talk about both photoanodes and photocathodes in this talk. I'll begin with the photocathode. And as I described, we'll talk about molecular constructs on the surfaces of these materials. So first, we'll talk about hybrid photocathode systems based on a nickel complex on silicon and gallium phosphide surfaces. Then a polymer brush approach, which allows for a higher loading capacity of these catalysts on those surfaces. And then move on to means of interface engineering in order to passivate defects on the surfaces of the semiconductors and to improve the corrosion resistance of those materials. And finally, I'll discuss a promising new photoanode material, bismuth vanadate, and some of our recent studies on carrier dynamics in those materials that ultimately can inform our synthesis procedures so that we can improve their performance. Okay, so beginning with molecular hydrogen evolution catalysts tethered to photocathode surfaces. There's actually a variety of hydrogen evolution catalysts available to us. For this particular study, we've chosen the nickel P2N2 complex, which is a hydrogenized active site mimic. Again, this is a hydrogen evolution catalyst. We're interested ultimately in molecular CO2 reduction, but since we don't have really high, well understood, let's say, CO2 reduction catalysts, we'll start by using these hydrogen evolution catalysts to tackle the scientific challenges that are associated with coupling that catalyst to the semiconductor surface. In any case, these are promising hydrogen evolution catalysts in their own right. They've been demonstrated to operate under aqueous conditions with high turnover numbers, high efficiencies, and tethered to surfaces. So in this case, from a science article in 2009, they were tethered to carbon nanotubes and operated electrocatalytically. That's in the absence of photoactivation. But nevertheless, it demonstrated their catalytic activity. Likewise, we need to choose the photocathode material that we want to use. There's a variety of p-type semiconductors that are available. Silicon, of course, is available in high abundance, and it actually has a conduction band edge that's well suited for hydrogen evolution. Another example material is gallium phosphide. The surfaces of gallium phosphide are maybe slightly less well understood than silicon, but it has a conduction band also that is very favorable for generating large photovoltages. So these two materials are the ones that we'll focus on for this portion of the talk. They're actually complementary. The silicon 111 surface is a very well-defined surface with a lot of literature behind it so that we can determine exactly what's going on in the system, whereas the gallium phosphide system represents a class of materials, namely 3,5 semiconductors, with a different surface chemistry than the silicon surface, but we would like to expand beyond silicon, so we'll investigate that as well. The synthetic procedure we use is outlined here. We first create a reactive semiconductor substrate, in this case on silicon with hydrogen terminal sites. Using a UV photoactivated process, we can bind an alkene linker molecule onto that surface that's protected on its end group. We deprotect it and link that to a catalyst that has an anchoring group tethered to it, ultimately resulting in a covalently grafted molecular catalyst on a semiconductor surface. I won't belabor the point here. We are able to develop very highly well-defined surfaces. So in this case, we have silicon. It has a native oxide when you receive it from the manufacturer. We can treat it with HF, completely remove that oxide, and from infrared spectroscopy, we do see that we have silicon-hydrogen SiH modes directly on the surface. These are the sites that allow us to do chemistry on the surface of silicon. In contrast, when we do the same treatment on gallium phosphide, we do not end up with hydrogen termination of the surface. Instead, we see that we are able to actually remove the native oxide. So we have a bare semiconductor surface, except it's then terminated by oxygen-bearing groups. And spectroscopic evidence points to a predominant coverage by hydroxyl groups. So now we're investigating the same chemistry, namely a reaction of this terminal alkene molecule with two different types of surfaces. One is hydrogen terminated, one is hydroxyl terminated. And what we find through both FTIR and XPS measurements is that the chemistries work similarly on the two surfaces, except we have a carbon-silicon bond to the substrate in the case of silicon, and an oxygen bridge bond to the gallium phosphide substrate for the case of the gallium phosphide. Following deprotection, we can react this with a nickel P2N2 molecule bearing an activated ester tethering group, and that results in a construct such as this. We can verify that this is formed similar to how we draw it using XPS. Here we see the nickel 2p region of the XPS spectrum that indicates that we have nickel in a 2+ configuration, consistent with what we would expect. Likewise, we've done FTIR spectroscopy. This shows us that the ligand environment of that catalyst, once it's immobilized on the surface, is similar to the catalyst in its as-synthesized form. Okay, so these spectroscopic measurements verify that we've synthesized what we aimed to. And for right now, I'm just going to leave the nickel system, but I'll come back to it in a moment. Another way of tethering catalysts to surfaces is based on a polymer brush approach. So for the case of the nickel system, we formed a self-assembled monolayer bearing active sites on which we could bind the catalyst. However, this naturally saturates at a monolayer coverage, that coverage being dictated by the size of the catalyst that you're attaching to the surface. That means you have a natural limitation, or it also means that you need a certain turnover frequency of catalyst in order to keep up with the solar spectrum because of the given coverage. So we thought maybe you can utilize the third dimension. We can grow up from the surface. Call it the Manhattan approach, maybe. So instead of being limited, since you can't grow sideways, you can actually expand and achieve a higher loading capacity on the surface if you use a polymer layer, not a self-assembled monolayer. So we utilize the self-initiated photography and photopolymerization reaction. In this case, what you do is you take one of the terminated surfaces, the hydrogen-terminated silicon, OH-terminated gallium phosphide, and in this case, you immerse it into a vinyl monomer that can undergo a free radical polymerization reaction. Under UV photoactivation, you get activated monomer molecules that can then abstract a hydrogen from the surface, leaving a surface radical that can initiate that reaction, and we get polymer brush growth off of the surface. It occurs much like this. So we have individual polymers coming up off of the surface. The thickness of these polymers can be well controlled simply by the illumination time of the UV light. In a real system, here we don't want to just use polystyrene like I showed on the previous slide. Here we use vinyl pyridine as our monomer. We immerse our activated substrate into that, illuminate the substrate, and this leads to the growth of a polymer brush layer on the surface. These pyridyl units can then be reacted with a cobalt catalyst in this case. This is another hydrogen evolution catalyst of a cobalt-oxime class. It starts off in a configuration such as this. Following reaction with the pyridine, you have displacement of one of these axial chloride units and binding in of the pyridine to the catalyst. Again, we can verify that we've created what we set out to create using surface-sensitive spectroscopic methods. In this case, XPS. Following growth of the polyvinyl pyridine layer, we see a single nitrogen signal associated with the nitrogen of the pyridine. After cobalt attachment, we see the emergence of a second peak. So we have still free pyridyl groups that have not reacted with cobalt. And the second peak, of larger intensity in this case, is actually from nitrogens that are coordinated to cobalt of the catalyst. Looking at the cobalt itself, we see a typical cobalt spectrum that's indicative of, in this case, cobalt 3+, which is what we would expect for the catalyst bound to the surface. That's indicated by the lack of satellite features in this XPS spectrum and the separation between these two peaks. Okay. Our goal is to do more than just create these constructs and synthesize them. We also need to demonstrate functionality and stability. So up till now, I've shown no current voltage characterization or photocatalysis curves. Here I show on the top right, though, the current that we obtain under photoillumination as a function of the applied potential. The dashed lines on the top show how these photoelectrodes, how these constructs operate when there's no light illuminating them. No current passes the interface. However, if we shine light onto this system, again, remember we're looking at a photocathode, so the minority carriers are electrons. Those electrons will be transported through this built-in electric field to the surface, and then be transported across the interface to the catalyst and drive the proton reduction. That whole process results in an electrical current, which we can monitor or display in a way like this, with current density as a function of applied potential. Under illumination, when we just have the polyvinyl pyridine functionalized gallium phosphide surface, we do get a photocurrent, but it requires much larger potentials to be applied to the surface. Here, 0 volts versus the real hydrogen electrode means this is the thermodynamic potential for hydrogen evolution. So at that potential with the gallium phosphide with the cobalt catalyst, we are generating hydrogen with no effectively applied overpotential. In fact, we're doing that with an applied with an underpotential. So given a photoanode that we could couple to with sufficient voltage itself, we should be able to spontaneously split water with such a device. The activity is stable once we have the polyvinyl pyridine on the surface. So this shows a stability measurement over a course of just 5 minutes here, but we can already see dramatic differences. The black line is the bare gallium phosphide electrode. This is 100% not stable. Over 5 minutes, its current density decreases by 80%. So that substrate is oxidizing under the conditions that we are generating hydrogen. In contrast, as soon as we have the polyvinyl pyridine layer on the surface, it's not a very good photoelectrode, but it's a stable photoelectrode. That's shown by blue here. In red, we have good photoelectrochemical performance, as shown by the curve on the top, and also stable performance. So this is an example of a catalyst derived from a molecular system attached to a photocathode that is functional and stable in aqueous environments. This is exactly what we're looking for. To understand this curve a little bit better, the difference between these two, we can look again at these band structures, or these band diagrams. For the case of the polyvinyl pyridine, we have no catalyst on the surface, but we do have interfacial defect states that can lead to charge recombination. So here again we have the electrons being accelerated to the surface by the built-in electric field, but there are surface defects that can trap those electrons and lead to recombination with holes. That means that we've absorbed a photon, we've created free charge, and then we've recombined it without doing any chemistry. That's a direct efficiency loss. When there's no catalyst on the surface, this process actually begins to dominate because you need to apply larger and larger potentials in order to separate this charge, prevent this reaction from occurring, and get to the overpotential required to drive the hydrogen evolution reaction. For the case of a semiconductor where we have the catalyst on the surface, such as in this red case, charge transfer is promoted to the catalyst, which means the recombination currents, the loss of efficiency, is reduced. And so we have an improvement of the overall performance of the photoelectrode by integration with catalyst. Okay, so that's two molecular constructs, one that's highly functional. I want to now return to the nickel system. You may have noticed that I didn't show any photoelectrochemical characterization like we did for the cobalt catalyst on the surface. And there's actually a reason for that. So we verified spectroscopically that we can form this construct here, shown at the top. However, these types of surface recombination centers on silicon, where we've done this type of synthesis, begin to dominate. So on the bottom are shown results from transient microwave photoconductivity. The name of the technique doesn't matter so much. It's a measure of surface recombination, or of a recombination time within the material. So on the bottom right is just shown that normalized response, and on the x-axis is time. So very short lifetime means that those carriers that are photogenerated recombine very rapidly. That red curve is just an oxidized silicon substrate. The black curve shows us after the HF etching. So we get a much longer lifetime on the silicon substrate. On the bottom left is shown this lifetime as a function of exposure time to an atmosphere. So in one case, it's exposure to buffered hydrofluoric acid. It's stable over time with a lifetime of about 70 microseconds. If we take it out of that HF, dry it off, and transfer it to sulfuric acid, which is where we do some of our characterization reactions, just that brief exposure to air results in a significant reduction of the lifetime of those carriers. So recombination centers have been introduced on the surface of the silicon. If you put it in air, you see that you have, over time, over the course of an hour, you get to a point where recombination totally dominates the properties of the surface of the silicon. In fact, the lifetime, the value that we measure, saturates at a small value because it's limited by diffusion of those carriers to the surface. That turns out to be the same lifetime that we observe after we do this reaction procedure on the surface. And the reason for that is that the molecules that we use to tether the catalyst to the surface have a certain size. So there's steric interactions that mean that we cannot saturate every single silicon surface site. Actually, we saturate somewhere between 10% and maybe 20% of the surface sites. The remaining sites still have a silicon hydrogen bond, which is not very stable, and over time, whether it's in air or under our aqueous environments where we want to do photoelectrochemistry, these will oxidize. And those oxidation events lead to recombination centers where electrons and holes easily and rapidly recombine, so we have complete loss of efficiency. So if we look at a similar photoelectrochemical characterization curve, an IV curve in this case, the silicon hydrogen, the hydrogenated silicon surface, looks quite good. It's completely unstable, but it looks quite good. Once we've done these reactions to attach catalyst to the surface, we have a complete reduction of the catalytic efficiency. We require much higher overpotentials in order to obtain the same current densities on those surfaces. So that led us to another line of interface engineering. And in this case, what we want to do is introduce a thin interfacial layer which can transport charge, but which also passivates surface states on the semiconductor. And one system that's quite promising is TiO2. And in particular, some of the recent advances in atomic layer deposition allow for atomic control at very, very thin layers that are completely conformal. And that's what we need if we want to also introduce stability into these systems. So here's an example of a p-type silicon with TiO2 on the surface. We've done photoelectron spectroscopy that can verify the work functions of these materials as well as the densities of states near the valence bands. So the valence band density of states is shown here. This onset here to the large feature in the spectrum is the TiO2 band edge. We also have a large density of states within the band gap, which we're currently investigating. This shows up as reduced titanium in the titania film. In any case, what we find is that application of a thin TiO2 layer does stabilize the photoelectrode, but the thicker you get with the TiO2, actually the better the performance gets. So here, you can barely see it, but the black curve behind this blue curve is for a 3 nanometer thick TiO2 layer. The blue curve is for a 40 nanometer thick TiO2 layer. This means right off the bat that we're not dealing with a tunneling process. So charge is transported through a 40 nanometer thick layer of TiO2 on the surface. If we combine this observation with our results from photoelectron spectroscopy, we can construct a bit of a band diagram where we have the p-type silicon with a downward band bending. And what we ultimately end up with is a TiO2 layer with a conduction band that lies lower than the conduction band of silicon. So we can directly inject charge into the conduction band of this TiO2. This is a perfect layer for separating the semiconductor from the electrolyte. This can be used for interface passivation if we use the right procedure to deposit the TiO2, as well as corrosion protection. And indeed, I won't show further results here, but we've begun the process of attaching molecular layers and molecular catalysts onto these modified photocathode surfaces that are stabilized by the introduction of an ALD deposited titania layer in this case. Okay, but if we're able to form a nice thin conformal coating on a photocathode surface, which is actually a milder reaction condition than the photoanode surface where we're really splitting water, why not try to do the same thing on the photoanode and see if we can actually induce additional stabilization of the photoelectrode? So we've tried this recently where we have, in this case, a PN junction in silicon. So charge is separated below the surface of the silicon by an electric field that we generate by changing the impurity concentration in the material. Onto the surface of that, we've deposited either ITO, in this case via sputtering, or TiO2 via ALD or sputtering. And on top of that, we've placed the catalyst. Now, this is a proof of concept, so we used iridium. Again, this is not one of the catalysts that we want for a JCAP device, but it's a highly efficient catalyst that will allow us to diagnose problems that we may be having at lower lying interfaces in the system. So here we have iridium directly on silicon, and the solid line shows as soon as you start testing this photoelectrode, it looks great. After 1 hour of operation, though, it's completely lost its catalytic activity. The silicon has oxidized and the iridium has fallen off the sample. In the second case, we've applied this interfacial TiO2 layer via ALD, again with iridium on the surface. It looks quite good and quite promising as soon as we begin measurements. But again, we do have some degradation after 1 hour and a half of operation. So it's not complete degradation, as is the case when you don't have the TiO2 layer at all, but it's not stable. Finally, we've deposited ITO onto the surface of the silicon. This, again, is more or less conformal on the surface. Iridium on the surface of that we've tested. You do require a bit of a higher potential to be applied in order to get the same performance. But after 4 hours of operation, it's performing exactly as well as it was when we first put it into solution. So we now have a silicon-based photoanode that can do water splitting. And impressively, this can be done also at pH 14. So for anyone that's worked with silicon, basic conditions, you will immediately oxidize or even etch the silicon depending on what you're using. Here we have a stable silicon-based photoanode. We can see this again in a plot here, which gives the the potential required to achieve 1 milliamp of photocurrent as a function of time. A black line that you can barely see here is if you just have N-type silicon with iridium on its surface. It is not stable at all. A few seconds, and you need to start applying much higher currents. For the p-n junction silicon with the iridium directly on the surface, it's a little more stable. This isn't going to keep operating, though. It's going to degrade quite rapidly. For the p-n junction silicon TiO2 iridium construct, it's much more stable. You see this is a completely horizontal line, and that's for this case, not even for the case with the ITO. The one thing that you may notice here is that you do require a higher potential to be applied in order to achieve this 1 milliamp current density. So there's room for improvement. That's the takeaway from that. The other takeaway is that that was all done with iridium, so let's maybe move on to something that's earth abundant. So we've done the same thing with cobalt oxide. And here we see similar curves where the cobalt oxide directly on silicon shows promising performance initially, but it degrades over time. However, if we introduce this interfacial ITO layer, we see that we have, now this testing was out to an hour, but it's quite stable again. In this case, we monitor the photocurrent as a function of time for cobalt oxide on these two types of surfaces. And we see with the introduction of the ITO layer, we do have quite stable operation. Some of these jumps here are likely associated with bubble formation on the surface of the electrode. Okay, so that was a demonstration of a stable photoanode based on silicon. That requires a means of stabilizing its surface against corrosion in the harsh electrochemical environment. Another approach is simply to use a semiconductor that itself is stable under these conditions. So that'll bring me to basically the final portion of my talk, where I'll discuss bismuth vanadate, which is a ternary oxide semiconductor that's promising for water oxidation, or as a photoanode. Okay, so this material, it has a number of different phases. The phase we're interested in is the monoclinic phase of bismuth vanadate, which has a band gap of about 2.3 or 2.4 electron volts. Shown here, we have an absorption spectrum of the material. There's an absorption onset right about 500 nanometers. This is where it starts capturing the solar spectrum. So it's not perfect. We lose everything below, so wavelengths longer than 500 nanometers. But for an oxide photoanode, this is pretty good. On the top right is shown the IPCE, which is effectively the external quantum efficiency of the device. We have a similar onset. Maybe it's slightly shorter wavelengths. But again, we're capturing quite a bit of the solar spectrum of this material. For an ideal photoanode, you would like to have a current density greater than 5 milliamps per square centimeter. Based on the band gap of bismuth vanadate of 2.4 electron volts, it's got a theoretical efficiency limit, or a theoretical maximum current density of 7 milliamps per square centimeter. Now, right now, that's not achieved whatsoever because we have problems with charge carrier transport in the material. But current densities between 1 and 3 milliamps per square centimeters are routinely achieved with this material. By improved materials design, materials synthesis, we should be able to get much closer to the 7 milliamps per square centimeter. Finally, this material is abundant and durable. Bismuth, vanadium, and oxygen are not rare materials. So it fits the requirement in the JCAT mission of being an earth-abundant system that's scalable and manufacturable. And the system, bismuth vanadate is stable between mildly acidic to quite basic conditions. Okay, so I highlighted the positive aspects of bismuth vanadate. What are the negatives? Well, there's some outstanding challenges with this material. Namely, charge transport, both minority carriers and majority carriers within this material need to be optimized. The fact that you have a maximum photocurrent density of 7 milliamps per square centimeter, and the best photoanodes that are reported right now are about 3 milliamps per square centimeter, means you have a problem with charge transport. It's not very catalytic, so it's not very good at oxidizing water. However, if you apply a catalyst to the surface and do it with care so that the interface is maintained to be of high quality, it can be a very good photoelectrode for water oxidation. 3, and what I'll be addressing mostly in the final portion of the talk, is that there's a lack of fundamental understanding of both the optical and electronic properties of this material. In fact, it's not even known if this is a direct or indirect bandgap semiconductor, which is one of the most fundamental things to know about a semiconductor. So additional scientific understanding about the properties of this material should allow us to improve the characteristics in both points 1 and 2 here. And then finally, there's basically a limited range of synthesis procedures that are available for forming this material. And they're mostly based on solution phase synthesis. So the light capture group, with Le Chen and Joel Ager at JCAP, are developing means of doing physical vapor deposition of this material, which should allow improved control over stoichiometry and for integration into spontaneous water splitting device. Okay. So I'm going to discuss some of our recent results on understanding charge carrier dynamics in the material using transient absorption spectroscopy, which should help us to understand how we can improve its interfaces with catalysts and to improve charge transport within the material. So real fast, just a quick introduction to transient absorption. This is a pump probe technique. So basically you start with a system. It's cut off a little bit, but on the vertical axis here is energy, and on the x-axis is the density of states within the semiconductor. So this is the conduction band, and this is the empty valence band in this example. We come in with a short pulse of light. This excites the system so that you have now a higher concentration of electrons in the conduction band and holes in the valence band. You then interrogate the sample with a second pulse of light to see how that pump pulse, or how this change of population affects the absorption spectrum of the material. So here, if we on the top see time, our pump comes in at time 0. If we now interrogate it at a time t1 after the pump comes, well, we have now no electrons at the band edge, at the conduction band edge of the material. That means it's going to absorb less light at the band gap of the material. So you'll have a negative going transient absorption, or a bleach, as we call it. You also have absorption related to the excited states. So these electrons in these holes that are now in excited states can absorb, whereas they couldn't when they were in the ground state. So we have additional positive transient absorption signals that we can observe. Now, that's the origin of the signals that we see. But what we're also interested in is the processes that lead to recombination and relaxation to the ground state. So we're interested not only in what the spectrum looks like at a given time, but the time evolution of that spectrum. And so if we interrogate this now at another time t2, where the sample is relaxed further, we see that there's less electrons in the conduction band, there's less holes in the valence band. So these excited state absorption features have reduced over time, and the bleach at the band edge has now reduced as well. So we can do transient absorption to measure carrier dynamics in the material over a wide time range. So from femtosecond timescales, where you have fundamental hot carrier relaxation processes, to picoseconds and microseconds, where you have these excited carriers recombining both electrons and holes directly combining across the band gap, as well as these carriers being trapped at defect sites. And then interestingly, we can also look to very long time scales, where the only carriers that still remain in the material are those that are charge-separated states. So in the case of a semiconductor light absorber, those are typically those that are near the surface, because in this electric field, for example, in this N-type material, we have holes that have now accelerated to the surface. And these are exactly the holes that participate in the water oxidation reactions that we care about. So it's these holes that we actually ultimately want to determine their lifetimes, and specifically what they're doing, where they're going, and how we're losing them in terms of efficiency. Okay, so what does transient absorption look like in BVO? Here's a typical transient absorption spectrum from a time scale of about 0 to 10 picoseconds. So in this plot, basically, it's a two-dimensional plot. You have wavelength on the x-axis and time on the y-axis. We're going to be taking slices through this two-dimensional plot to look at what's going on in the material. So this horizontal slice gives us a spectrum, a change of absorption at a given time after the pump, where we have this negative going bleach feature. This is that band edge bleach that I was discussing on the last slide, and positive absorbances, which we need to identify. If we take kinetic traces of some of these interesting features, we see a few things. Again, we have the bleach feature, which is given by a negative transient absorption. We have positive going features. We have some oscillations here, which I won't actually talk about today. This is due to coherent phonon coupling to the carriers, which is an interesting physical process, but it doesn't have very much to do with photoelectrochemical performance. So our first task is to identify the origin of these features. One way to start analyzing what's going on is to do a pump power dependence. So let's look at two of of the spectral ranges. One would be where this transient bleach is occurring, and one would be this sub-band gap induced absorption, so this positive going transient absorption. Here we've increased the pump power, and again, here we've increased the pump power. So this is a sub-band gap response, and this is a band edge response. And what we see is that there's actually a nonlinear component to the increase of the transient absorption that varies with increasing pump power. Not going into a lot of details, but that can be attributed to Auger recombination under these high injection levels. So in that type of a process, you have high concentrations of electrons, say in the conduction band, holes in the valence band. They can exchange energy with other carriers in the conduction band. You have a recombination. The energy released from that recombination event is absorbed by another carrier. So that can occur from free carriers. It can also be trap-assisted. So this is a trap-assisted Auger recombination process. It turns out this actually plays a significant role in bismuth vanadate of the quality that we have right now. But again, I won't go into too much detail about that today. The key point, though, is that these responses are associated with free carriers because it's an Auger recombination that's occurring. That allows us to, again, attribute this bleach, as we would expect, to the band edge bleach, because now we have an excited state population of electrons in the conduction band and holes in the valence band that prohibit optical absorption across that band gap, or at least decrease its probability. The sub-band gap response, initially you could think that you wouldn't see anything below the band gap of the semiconductor. There's no allowed states there. Well, that's true, but this is an excited state absorption. So what we're having here is either electrons or holes that are free within the band gap absorbed. The task, though, is to determine which one, is it electrons or holes, that's responsible for the spectral signature. We can do that using another technique, in this case in the steady state. Here we do spectroelectrochemistry. So now we're operating in solution. We have a photoelectrode, and we apply an electrochemical potential. And we compare the absorption spectrum when we apply a positive bias versus the open circuit potential of that photoelectrode, and a negative bias. Another way to think about it is we measure the absorption spectrum when we've accumulated holes in the electrode and when we've accumulated electrons in the electrode, and look at that in comparison to one where we've done neither. So in this case, this positive applied potential results in a positive absorption feature that ranges from about 425 nanometers or so out to beyond 600 nanometers. That corresponds well with this positive transient absorption that we observed in the transient absorption measurements. And that allows us to say, under these positive potentials, we've accumulated holes in the material. We can now say that these near sub-band gap absorption features are related to excess holes. That's very important for this material, because these are exactly the carriers that we care about in a photoanode. It's the holes that are transported to the surface. It's the holes that are transported across the interface of that photoanode to the electrolyte, and then ultimately drive the water splitting reaction. So now we have a spectroscopic handle in which we can trace the progression of these holes, and as they recombine, we can monitor that. We can look as a function of material quality, interface quality, etc., on how these holes live over time. So again, returning to the transient absorption spectrum of the material, we see this ground state bleach due to the filling of the bands of the semiconductor, and we see a free hole related absorption signature. Going farther out here, I won't discuss it today, but we also have a signal associated with free electron absorption. These two gray features, which appear to be dominant in the spectra, I won't discuss in great detail today. They are important. They're related to trap states, most likely. We're investigating them, and we have some good ideas of what they are. But the fact that already we can identify the free hole signature is the important point, and will allow us to go further. So all of what I was talking about was on very fast time scales, 0 to 10 picoseconds. If we're talking about the lifetime of the carriers, not the Auger lifetime, so that's one particular recombination pathway at very high carrier concentrations. We care more about what the bulk lifetime in this material is. So there we'll go out to measurements on hundreds of nanosecond timescales, where we actually do have recombination of these carriers with defect states or with the opposite type carrier. And we measure all of the measurements that I showed so far were on a certain class of materials that we had synthesized, and they ended up being characterized by a bulk hole lifetime, that positive going sub-band gap response. The lifetime of that was about 3 nanoseconds. However, it turns out with some more of the modern samples from JCAP that this lifetime, as would be expected, is strongly dependent on the quality of the material that we're measuring. And now we have samples that are routinely exhibiting lifetimes that are out beyond 25 nanoseconds. So already that's a large improvement in performance. That, I might also add, corresponds directly with the quality of the photoelectrode. So it's photoelectrode efficiency. You'll also notice the dominant feature here. That's the one I'm not talking about. That has a lifetime of about 250 nanoseconds. So there's a trapped state that very slowly returns to equilibrium compared to the other processes occurring in the material. The next thing we're interested in, though, is what's the effect of the surface. So these are bulk lifetimes. That's important. That tells you about what volume of material or what length scale of material near the surface is going to be active. So if a photon is absorbed near the surface, that can actually participate in doing chemistry rather than recombining. But we're also interested in what occurs when that carrier gets to the surface. So for that, we have to go to the longer time scales. Again, microseconds out to even seconds. This is a transient absorption spectrum now going from exactly that time scale, microseconds out to milliseconds. And what we've done is measured the response of that photo hole signature as a function of time at two different applied electrochemical potentials. This is now a transient absorption, an in situ transient absorption measurement at long time scales. So when we don't have an applied bias which purposefully accumulates holes at the surface of the material, we do still have, even at these very long lifetimes, a very small signal left of those holes. So there are some photo holes that are making it to the surface and staying there. If we apply a positive potential, we then increase this electric field, we increase the driving force for this charge separation to occur. We get accumulation of holes at the surface, and our electrons are swept out away from regions where they can recombine with the holes. That leads to a much larger accumulation of holes on the material, and we have an almost order magnitude increase of the concentration of those holes on that surface at a given time out to millisecond time scales. Those are exactly the carriers that we require for doing water splitting. So that's a great sign that we can actually monitor what's going on with those. The next task will be to determine what the impact of different surface treatments on the material is on these lifetimes. I'll get to that right at the end of this talk. But now I'll turn to one other thing that we've been doing at JCAP with bismuth vanadate, and that I mentioned that the light capture group, headed up by Joel Ager, is developing new methods of physical vapor deposition of bismuth vanadate. That enables a new level of stoichiometric control that's not available from the solution phase synthesis procedures. So here's an example where we have a stoichiometric film of bismuth vanadate. It's slightly rich in vanadium. That's in order to get the N-type doping that we need for a photoanode. So this is a bismuth vanadate stoichiometric film. This is one where it's too vanadium rich. So it's too enriched in vanadium. What we observe here from XPS is that we have a single phase material of bismuth vanadate for the case when we have the stoichiometric ratio. That's as expected. When we have an excess of vanadium, we have phase segregation, though. We form vanadium oxide together in the bulk with bismuth vanadate. We can look again at the current voltage curves for these photoelectrodes. We see the single phase bismuth vanadate operates quite well. This is what we expect. As I said, we get something around 1 milliamp per square centimeter with many of these photoelectrodes. However, when we look at the phase segregated material, this is a terrible photoelectrode. We're getting almost negligible current densities through the interface. This is not suitable for the systems that we want to study. So we've done transient absorption on this to see what the effect of that phase segregation is on the whole lifetime. And we found something that was completely counterintuitive, and that's the whole lifetime is dramatically increased when we have the phase segregation within the material and this very poor photoelectrochemical performance. Whereas we have about the 3 nanosecond lifetime observed for the material where it's operating quite well from a photoelectrochemical characterization standpoint. The reason for this is a bulk charge transfer within the material. So regions of bismuth vanadate can be photoexcited, but the electrons can then be transferred within the bulk to regions of vanadium oxide. This is great. It leads to large whole lifetimes because there's a barrier towards recombination physically. But we can't extract that charge to the surface to do the chemistry that we want to. Okay. However, I will note that we can now reproducibly synthesize films of this quality But it means also that we need to always keep track not only of what this whole lifetime is, but that needs to be tied directly to what the structure of the material is at the same time. Okay, finally, I mentioned that bismuth vanidate's not very good at performing water oxidation in and of itself, so we need to integrate this with a catalyst. So in this work, this is again current density versus voltage curves, where we have the bare bismuth vanadate surface versus one where we've integrated a cobalt phosphate layer, which is a good water oxidation catalyst. We see again a significant improvement of its photoelectrochemical performance characteristics, given by the red curve here. And we wanted to determine whether, now that we have a handle on these holes that participate in the water oxidation reaction, whether we can observe that change of photoelectrochemical performance with our transient absorption spectroscopy. And it turns out we can. So when we have bismuth vanadate that's bare, you get this blue curve. When we integrate the cobalt phosphate onto the surface, we have a much more significant accumulation of holes on the surface of the material. Now, I originally thought that's completely counterintuitive. I would have thought that if you put a catalyst on the surface, you would have charge transfer of the hole onto the catalyst and drive water oxidation with a higher current density at a given potential. So you should have actually those photocarriers being swept out of the semiconductor. This is a cooperative effect. It turns out that the application of the catalyst onto the surface of the bismuth vanadate actually passivates those surface recombination centers. So you have both the catalyst acting in a catalytic manner, so improving the kinetics for water oxidation, but also it's preventing or reducing the probability of charge carrier recombination on the interface, at the interface. This is actually consistent with what's been observed with some other materials, hematite and tungsten trioxide in particular. But it means that actually the task of integrating a catalyst on the surface of BVO might not be as challenging as it would have otherwise seemed. Okay, so that's all I basically wanted to say today. So I hope I've kind of convinced you that we're kind of simultaneously attacking many aspects of the system to ultimately end up with a combined solar fuels generator. So this means that we have to interface both molecular catalysts on the photocathode surfaces, solid state catalysts on the photoanodes, and understand all of the processes of getting that charge from where the photons are absorbed to where they're actually, those carriers, those charge carriers, are going to do chemistry. So finally, I'd like to thank the people involved, particularly in the molecular nanoscale interfaces project. Heinz Frey, who just introduced me, is the project lead of the interfaces project. I'd also like to give a special thanks to Gary Moore, who's a staff scientist that I work very closely with. He's responsible for all of the synthetic efforts and much of the work on the molecular linkers, basically, along with his postdoc, Alexandra. Jin Hu is a postdoc working with me on a lot of the atomic layer deposition and solid-state interface engineering. And Jonathan Nip is a new master's student that's actually done a great job of taking a lot of the transient absorption data. We'll also have another postdoc join us at JCAP in just a few weeks, who's already, through discussion, provided a lot of insight into the business candidate. Furthermore, the light capture group at JCAP, headed up by Joel Ager, and with a lot of work from his postdoc, staff engineer, Le Chen, have made great advancements into the synthesis of bismuth vanadate and characterization of those materials. And Adam Schwartzberg has been very open at the Molecular Foundry with advising on atomic layer deposition processes. So, thank you.
Thank you. Do we have any questions from the audience?
Yin, when you have the sort of titanium dioxide layer between the NP silicon and I think it was the iridium oxide catalyst. Mm-hmm. Now, how does the whole actually, is the whole transferred to the titanium oxide? How thick is the titanium oxide? Because the valence band is far too positive,
There's various
right?
thicknesses. Yeah, you can see that actually when this is on the p-type. So this is on the photocathode. If you look at where this Ti2 is, regardless of the silicon, valence and conduction bands are way up there. So this works on the photocathode side, right, to get electron transport. But you're absolutely right. To get hole transport, this should be a huge barrier on the surface. So it does have to be rather thin. You do see here that you require a higher applied potential when you have the TiO2 there, but the system becomes much more stable. So that's not the only point, though. So it's most likely a tunneling process. However, when we do our photoelectron spectroscopy, we do see that there's a broad distribution of states. This is ALD deposited TiO2. It's not high quality titania. So there's likely a lot of defect states that we're actually investigating their role in charge transport. There could be hopping processes that occur. It's not yet clear whether these mid-gap states in TiO2 are actually beneficial, so they permit improved charge transport through hopping, or they're detrimental in that they lead to carrier trapping. But you do, in any case, get current, a whole current, through the TiO2. Question is simply what potential you need to apply.
Do we have other questions?
I had a similar question to Heinz. And did you try to optimize the thickness of the TiO2 for, you said that there was a range between 3 nanometers and 40 nanometers.
Yeah, so the 40 nanometers on this photoanode side would not be a good thing. So I think you would completely shut down photocurrent. On the photocathode side, however, once you inject the charge into the conduction band of the TiO2, its ability to be transported to the surface is mostly dictated by the quality of the TiO2. You could effectively have a very thick layer, and that should pose no problem. So for dye-sensitized solar cells, you have dyes that are on the surface. They inject charge into the band of TiO2, the conduction band of TiO2, and that charge can be transported through the whole film. So it depends on the energetics. On the photocathode side, we just need to worry about the quality of the TiO2. On the photoanode side, we need to really make sure that we keep this as thin as possible so that we don't have too much of a hindrance to charge transport across the layer.
Thanks.
Hi, Ian. For your last example, when you combine the cobalt oxide catalyst with the BVO, do you have any evidence that the catalyst is actually doing catalysis on the surface or just doing the passivation on the surface?
That's an excellent question. So that's, right now in the literature, a controversial issue when you talk about hematite. This effect has not yet been reported on BVO, but for the case of hematite, the transient absorption measurements primarily tell you about passivation. Transient photocurrent and transient photovoltage measurements should allow you to, combined with the transient absorption measurements, say something about the relative role of catalysis on that surface, or if it's just a passivation effect. Those types of measurements are ones that we have envisioned right now and will be pursuing. But these measurements themselves are mostly sensitive to the degree of accumulation of holes at that surface. So this says pretty much unambiguously that you do have hole accumulation at that surface, and that does imply that you have a passivation effect. It says nothing about whether catalysis, whether the cobalt phosphate is actually improving catalysis of the surface. Though the known poor catalytic efficiency of bismuth vanadate suggests that this co-PI is actually acting as a catalyst on the surface and not just a passivation.
Do we have other questions?
I was just curious what the scientific motivation behind making the polymer brushes as opposed to maybe inorganic long, high aspect ratio structures that could give you equal surface area.
Right. So the polymer brush allows the attachment of these molecular catalysts using well-defined surface chemistries, and it provides a really flexible environment for that catalyst to go through the intermediate states that are necessary to be catalytic. So as we go to CO2 reduction catalysts, these could be complex systems. You might actually also envision having multiple catalysts in the same film to perform different stages of this overall process where you need something like 6 or 8 protons to be added. So that's the idea behind this. For a solid state system where you simply have a higher surface area, you could actually combine the polymer brush approach together with that. So you would have all of this polymer closer to the surface, or within the volume of the material effectively, and you would have a true hybrid system. I think that's also a promising approach. Certainly we've looked at systems of high surface area of the semiconductor in and of itself, and that does tend to improve things. However, the fact that we really retain a soft environment for this cobalt-oxime-based catalyst likely does actually allow it to function more like it would in its homogeneous environment. I won't say that it is doing that, but it seems more likely.
Yeah, I also had a question about the polymer brushes. I was wondering how conductive those are for electrons and how much you gain from stringing more and more catalytic groups along those.
That's an excellent question. It's a fascinating thing that I think we need to address. The backbone is not conductive. So the question then arises, what is the charge transfer length into this polymer brush layer decorated with catalyst? Is it still just 2 nanometers, so you have basically the first layer that's actually active and the rest of the catalyst is basically dead? Is there actually a hopping mechanism that can get the charge out farther into the catalyst? Is the flexibility of the polymer enough just to get, in kind of a stochastic way, eventually some charge transfer processes, or to get the catalyst within a tunneling length, basically, of the surface? We don't know the answer to these questions right now, but I think that's a really interesting area of research to pursue with that type of system.
I think we have time for one more question. All right. Thank you very much, Ian, for presenting. And please join us on Tuesday, August 13th for the next Science and Tech Talk. That will feature Paul Adams. Thank you.
Thank you. I hope so. Oh, wow.